I've got two theorems up on the board. This is information that I gave you earlier when we were looking at algebraic ways of evaluating limits, but now the book is just formally stating it. Okay. So Theorem 5 tells us that polynomial and rational functions are continuous on their domains. And then Theorem 7 repeats that information. It reminds us that polynomials and rationals are continuous on their domains, and it just adds to the list. So root functions are continuous on their domains. Now for that, we did need to modify our definition for even roots, because even roots are going to have as their domain this interval from 0 to infinity, including that finite endpoint of 0. So when this is our domain, which is the case for any even root, we're going to have that we're continuous from the right at 0 and continuous using two-sided limits everywhere else in the domain. Trig and inverse trig functions are continuous on their domains. Exponential functions, remember an exponential function is like y equals e to the x or y equals 2 to the x. That's when the variable is in the exponent position. And then log functions as well are continuous. Now, I've added here the absolute value. I sort of put that in purple because the book doesn't mention it as part of this theorem. But that's the other type of function that we'll encounter on a fairly regular basis, and it is also continuous on its domain. All right, the next couple of theorems we're going to have are going to tell us that if we start with continuous functions and we combine them using either arithmetic or composition, we're going to get a continuous function as well. So I've now got up on the board the two theorems that tell us that if we combine continuous functions, we will get a continuous function. Theorem 4 tells us that if we combine continuous functions using arithmetic operations, addition, subtraction, multiplication, or division, we will get a continuous function. So it says if f and g are both continuous at a, and then c is just going to be a constant, the following functions are also continuous at a. F plus g and f minus g, those are the two functions I can build using addition or subtraction. We've got two versions of multiplication, c times f, so that's multiplying the continuous function f by a constant c, or f times g, that's multiplying two functions that are both continuous at a together. And then division, f divided by g, that of course would be assuming that the denominator isn't 0. So if we're talking about continuity at a, that would mean that g of a can't be 0. Okay, excellent. Now the theorem is stated for continuity at a point a, but of course if functions are continuous at all values in their domain, then they're continuous on their domain. So if I have two functions f and g that are continuous on their domains, when I add them, I'm going to get a function that's continuous on its domain. So this can be extended to functions being continuous on their domains. Sometimes when I combine functions, that affects the domain, but if f and g were continuous everywhere they were defined, then these resulting functions will be continuous everywhere they're defined, with the possible exception of places that make, well, with the definite exception of places that would make the denominator of this fraction 0. All right. Theorem 9 basically says the same thing for function composition. So if g is continuous at a and f is continuous at g of a, then the composition f of g is continuous at a. Let me just remind you, f of g of x means f of g of x. I actually prefer this notation. I plug x into g, whatever that result is, that's what I plug into f. Okay. And again, this can be extended to if I compose functions that are continuous on their domains, I'm going to get a function that's continuous on its domain as well. Okay. So these theorems are very, very powerful because almost every function that we work with on a regular basis can be built out of those continuous functions using some combination of arithmetic and function composition. So for example, the square root of sine squared x minus 2, whoops, let's not do that. Let's make that plus 2. The minus 2 wouldn't have been defined because the biggest sine squared can be as 1, and I can't have a negative under the radical. Okay. But notice, sine squared of x, I could view that either as a composition, plugging sine into the squaring function, or it's just a product. That's the product of sine times sine. Then I'm adding 2. 2 is just a constant function. Okay. And I'm plugging that into the square root function, so that's a composition. So this function is going to be continuous on its domain. So what these theorems tell us is basically most of the functions that we work with on a regular basis are continuous on their domains. So where we're going to run into discontinuities, and those are the limits that are more interesting to evaluate, are going to be at places that are not in the domain of the function, or if I have a piecewise function, at the places where the rule changes. Okay.